Welcome! In this video, we want to know why the Lagrangian method works. Recall that the Lagrangian method tells us that if we want to find the maximum or minimum of the function f of xy subject to the constraint equation g of xy equals to c, we have to solve the following system with three equations. Namely, the first equation is f sub x of xy equals lambda times g sub x of xy. The second equation is f sub y of xy equals to lambda times g sub y of xy. And the third equation is the constraint equation itself, g of xy equals c. And the unknowns are x, y, and lambda. In the last video, we used two examples to illustrate that if we think of the graph of f as a mountain, then the constraint gives us a mountain path. To find the maximum under the constraint means to find the highest output point on this path. For example, this purple line is the constraint equation, and this yellow line is the mountain path. On the surface, fxy equals to x squared plus y squared for those points which satisfy the constraint equation. In the coming explanation, let us focus on the situation when the objective function is f of xy, that is having two input variables, and we have one constraint equation, namely gxy equals to c. We can explain how the system of equation comes out by visualizing the situation on the two-dimensional plane. First of all, if we draw the constraint equation g of xy equals to c on the xy plane, it will be a curve. For the objective function z equals to f of xy, it is a three-dimensional surface. But if we consider its cross-section at a fixed level of z, it gives a curve. We can project each of these curves back to the xy plane and get different curves. In each curve, those coordinates x, y are points that will give the same level of output value for f of xy. They are called level curves. Altogether, it is a contour map. If the curve g of xy equals to c crosses one level curve and then crosses another level curve, it means that when we walk along the mountain path, we are experiencing an increase or decrease in the height of the mountain. For example, in this diagram, if we walk on the path in this way, in the three-dimensional situation, it means that we are climbing up the mountain z equals to f of xy and then going down. We can draw more level curves to visualize the situation. When an extremum of f is reached under the constraint g, the constraint equation g of xy equals c touches one level curve fxy equals to d. There will be no crossing of the level curve because otherwise you could have reached another level curve and experienced a change in the height. This is another place where the constraint equation touches the level curve. We shall determine the tangents and the gradient of the function g of xy to give further explanation. For a given constraint equation g of xy equals to c, the value of y depends on x under this constraint. For example, if we have 2x plus 2y equals to 10, that means y equals to 5 minus x. That means y depends on x in this way. In general, we can regard g of xy equals to c as an implicit function. Differentiate both sides of g of xy equals to c with respect to x. We get this equation: g sub x plus g sub y times the derivative of y with respect to x equals 0. If we write u as the vector 1i plus dy by dx times j, and write the vector v as g sub x times I plus g sub y times j, then this equation means that the dot product of v and u is 0, meaning that these two vectors are orthogonal to each other. The vector u is the tangent vector of g of xy. The vector v is the gradient of g of xy. The vector u is the tangent of the curve. For example, in this case, if g of xy is 2x plus 2y, then we have tangent vector to be I minus j and the gradient of g to be 2i plus 2j. For another example, if we have g of xy to be x squared plus xy plus y squared, and this constraint equation is gxy equals to 3, then after taking this derivative, we will get the tangent vector in this case to be this vector and the gradient of g to be this vector. We have tried the points at 1, 1 to see what is the result for this tangent vector and the gradient of g. The tangent vector is parallel to the tangent of the curve at that point, and the gradient of g is always orthogonal to the tangent. The following diagram shows the gradient of g and the tangent vector at different locations. The same situation happens on each of the level curves for f of xy equals to d. The gradient vector of f at a certain point is always orthogonal to the tangent vector of f at that point. The diagram shows the tangent vector of f of xy and the corresponding gradient of f of xy at different locations. At a particular point x0, y0, when an extremum of f is reached under this constraint g, the constraint equation gxy equals to c touches one level curve f of xy equals to d1. It means that the tangent line is the same, meaning that the tangent vector of f and tangent vector of g at this point are parallel to each other. This will imply that the gradient of f and gradient of g at this point are parallel to each other. Therefore, we have the gradient of f at this point equals to lambda times the gradient of g at this point, where lambda is a constant, which is a real number. It is the same condition here. This gives the system of equation we need to solve for and to obtain all those potential points at which the constraint curve g of xy equals to c touches the level curves. We can refer to the examples again. We have solved them in previous video. We can explain them using the level curves. This is the first example and the solutions were given in the last video. This is the corresponding three-dimensional graphs for the objective function fxy equals to x times y and the constraint equation 2x plus 2y equals to 10, which is given on this two-dimensional plane. When we solve this system of equations, it means that we would like to locate the points x0, y0 at which the gradient of f equals to a multiple of the gradient of g, and it is lying on the constraint curve g of xy equals c. We have solved that it happens when x equals to y equals to 2.5 and lambda equals to 1.25. It means that at this position, the gradient of f and gradient of g are parallel and pointing at the same direction, and the gradient of f is 1.25 times as long as the gradient of g. And the output of this point is equal to 6.25. If we used the constraint equation x plus y equals to 5 instead of 2x plus 2y equals to 10, then the lambda we obtain in this system of equation becomes 2.5, but the position where these two gradients are parallel to each other is still the same, and it locates at x and y equals to 2.5, and this gives the same output f of 2.5 equals 6.25. You can also refer to this change where I changed the constraint equation to be negative x minus negative y equals to negative 5 instead of the original constraint equation, but they mean the same constraints. This time, the two gradients are still parallel, but they are pointing at opposite direction. And the lambda we get this time is negative 2.5. So the value of lambda here may change depends on how we rephrase our constraint equation. But the important is that at the place where extremum occurs, the gradient of f and the gradient of g are parallel. You can also refer to the second example on page 3, which we have performed in last video, for the explanation when we refer to the level curves. And the details of the solutions are given here. Please refer to it by yourself.